Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Okay, in previous section, we just talked about various different I/O operations. Okay, when an application program issues an I/O instruction to the operating system, then the operating system invokes the device driver, and then the driver software going to communicate with the controller, in particular device driver in this, write the parameters to the operands register and write the opcode to the opcode register, right? And then set up the busy registers, and then it can start the data transfer between the device and the buffer. Okay, and then later on, so once this operation is done, then it can actually inform the driver, says, okay, I'm done. So the driver check the status and then start to copy the data from the buffer in the controller into the main memory. Okay, so during this time, so the buffer going to be used, okay, to temporarily hold the data, which will actually transfer between the device and the main memory. Okay, so now in this section, the section 9.2, we're going to talk about the data buffering and the caching. So recall in section 9.1, we discussed the programmed I/O, and in particular, we used the example of programmed import, like with polling, with interrupt, or with DMA. Okay. So remember, so we used the device controller, okay, to perform these I/O operation. Now the controller has some registers, right? So operands, opcode, busy, and the status registers. And in particular, the controller has a register called a buffer. Okay, so a buffer is a register. Okay, now this register is used to hold the data. Okay, now in this particular case, it just holds the data from the device, like an import device. Okay, so just keep the data from the import device, copy it from the import device. Okay, and then later this data will be removed and from the buffer and copied to the main memory. Okay, so we just mentioned that the buffer is used. Now in general, a buffer is a register or an area of main memory, so used to hold data generated by a processor, producer process. So the producer process is a process that create the data and save it in the buffer, or an import device, like in this case, the case we just talked about in the previous slide, previous section, and then removed from buffer at the later time by consumer process or an output devices. Now, in this particular case, we talk about the data from in the buffer was removed by a device driver, right? So it removed from the buffer and copy into the main memory. Okay, so then the buffer is free, and then the device controller can actually start to copy the data from device to the buffer, and then the process can repeat. Okay, so buffer is actually widely used, not just in the controller. Also, buffer is also used in part of the main memory. Okay. Now, depending on the intended use, a single buffer can hold one character at a time or a large block of data. So you may have a single buffer, or later on we're going to talk about some kind of multiple buffers. Now let's take a look at the examples of the use of buffers with keyboard device. Now a keyboard generates characters one at a time. So when you press the keypad on the keyboard, a character is generated. And then when you press the keypad again, another keypad, then another character is generated. And so one at a time. But typically a user process may wish to receive the data only as complete lines. Okay, so they don't want to receive one character and then receive another character. So in that case, the keyboard driver can accumulate multiple characters in the buffer. Okay, now, and then they edit the data in the buffer based on special characters received. Okay, for example, if they try to type a couple of characters and then one of the characters is typed wrong, so they want to correct it, so they're going to move the cursor to the location by type the special character like left arrow. Okay, and then they press the backspace and then they type the correct character and then type the right arrow, right? So they can do this, okay, and then they do the operations in the controller buffer. Okay, now until all the editings are done, then they're going to actually press the enter key to send the data in the buffer to the main memory. Now in that case, the driver is said to operate in cooked data mode. Okay. Now in another case, the driver passes all characters to the application unchanged, including the special characters. Now this is called the raw data mode. Let's talk about each of these modes. Okay. So let's say we have a keyboard. Okay, so now we have a keyboard controller, and the controller has a buffer called a controller buffer. Okay. Of course, the controller may have other registers like operands, opcode, but we just don't actually need to list it here. We just actually emphasize the controller buffer. And then the controller buffer is actually, eventually going to send the data in the controller buffer to the memory. Now, before actually it sends to the memory, it first actually going to move the data from the controller buffer to the called memory buffer. Okay, and then from the memory buffer to the application. So the controller buffer over here, of a keyboard decouples the operation of keyboard from the driver. Now here's the driver. Okay, so the keyboard driver. So it's a piece of software, right? Okay, so the controller buffer decouples the operation of the keyboard over here from the keyboard driver. Okay, and the driver may be blocked when the data is transferred from keyboard to the buffer, so the keyboard driver will be blocked until the transfer is done. So then the keyboard driver can access the controller buffer and send the buffer data into the main memory. Okay, now the memory buffer over here is another buffer. Memory buffer decouples the driver, okay, from the application. So the buffer also allows the driver to allows the keyboard driver to pre-process the input lines. So that means the driver can actually, edit the data in the buffer to correct all the errors, and then before passing control back to the application. Okay. So for example, let's take a look at the example of, for example, the user wished to type a character text. Okay. But user made a mistake. So user type T and then move the T to the memory buffer T. E it's supposed to be X, but the user typed the wrong character TST. So the TST is moved to the memory buffer, sent to the memory buffer. And then the user wants to correct it, right? Because the S should be X, not S. So then the user actually basically type special characters. Okay. So the user press the left arrow key. Okay. So let's see. User types the left arrow key. Okay, and the left arrow key is sent to the memory buffer, and then the user type the backspace key, and then type the correct character X sent to the next, and then type the another arrow key to the right. Okay. So in that case, in the original character TEST was sent, and then user find out there's a mistake, so they press the back, the left arrow, so move the cursor before the T and after S, and then press the backspace to erase the S and type the X, and then move the cursor back. Okay, so all these special keys are sent to the memory buffers unchanged. So that's called raw import mode. Okay, raw import mode. So in that case, all the characters, including the special characters, are sent to the moved to the main memory buffer. Okay, that's raw import mode. Okay. Now let's take a look at another case. So then we're going to talk about a cooked import mode. So suppose we have a keyboard here, and then we have controller, buffer, and then we have a keyboard driver, right, running over here. Okay, and then you have the memory buffer. And then the application. So initially, user typed wrong, okay, typed TST. And then user find it's wrong, so that's initially it's a TST. And the user is find it's wrong, then you're gonna type the, back, the left arrow. Okay. Now in that case, you're gonna actually move this cursor to over here, and then type BS and type X. So you can actually type once it's typed BS, you can actually erase the value S, and then type X. So you're gonna actually put the let me use different color. Put the X in there. Okay, and then move the um, right arrow. So you're gonna move the cursor to here. Okay. So in that case, that's called a cooked import mode because all the special characters, like here, um, left arrow, backspace, and X, and right arrow, all these things are basically not actually transmitted to, moved to the main memory buffer. Only the final result is moved to the main memory buffer. That's called cooked import. Now, in a producer consumer situation, sharing a buffer. Now, for example, if we have a buffer in the device controller, so the device controller can use the buffer and copy the data from, let's say, okay, so we have a device controller, right? And device controller has a buffer, right? And the buffer actually, and here's the device. So now the buffer basically is regarded to be shared by the device and also by the driver, right? Device driver. Driver software. Okay. So now if the controller is actually move the data from device to the buffer during this time, now the driver should be blocked because the driver cannot access the buffer because buffer is currently receiving the data from device. And then also, so when the driver actually completely send the data to the buffer is full. If the buffer is full, and then if the buffer is full, then it use the extra flag, like just tell the driver, say I'm free now, so you can actually access the buffer data. So the driver basically unblock itself and try to access the buffer and then copy the data from the buffer to the memory, right? So in this case, buffer is shared between the device and the driver. So when device is using the buffer, the driver should not be able to use the driver buffer. But if the driver is actually access the buffer, the device cannot, the controller cannot copy the data from device to the buffer. So only one, the buffer can be used only by one. Okay. So that's the problem. Okay. So now the buffer swapping is a technique that allows the operation of a producer process and a consumer process. Okay, so the producer process and the consumer process, okay, to and the consumer to overlap by using two buffers. Okay, instead of one buffer, we use two buffers. Okay, so for example, if we have two buffers here, okay, so then a device can copy the data to one buffer and the driver can copy the data to the memory from another buffer. If you have a buffer 1, buffer 2, right? So that's something we're going to talk about. It's called buffer swapping. Okay, so before we talk about two buffers, let's talk about the consumer and the producer and the consumer with single buffers. Okay, let's say suppose actually here's a consumer and we have a producer here. Okay, so now in this case, if we use polling, when the producer is producing, okay, the item and fill the buffer. So when producer actually fills the buffer. And then the consumer will not be able to use the buffer because producer is actually use the buffer and fill the buffer. Now, when the producer complete the feeding of the buffer, and then the consumer going to be kicked in and copy buffer, copy the data, and remove the data from the buffer. And once this is done, the producer can actually, fill the buffer again. And then the consumer going to copy the buffer again. Okay, so you can actually repeat this. Okay. So in that case, when the producer is feeding the buffer, okay, when the producer is feeding the buffer, the consumer in this case probably going to actually pull the data, right, from the buffer. Say, are you ready? Are you ready? And the producer, I'm busy. I'm feeding the buffer. So this time, the consumer time is wasted. Okay. Okay. Now, on another hand, when the consumer is copy the buffer, the producer's time is wasted. Okay. Okay. Again, the consumer time is wasted. Again, the producer's time is wasted. Okay. So that's the scenario with actually single buffer. Okay. Now let's use two buffers. Okay. Let's use two buffers. And then we can do the buffer swapping. Okay. Now here again, it's a consumer and producer. Okay. Now when the producer is actually first filling buffer 1, both buffers are empty. So when the producer filling buffer 1, okay, now the consumer's time going to be wasted, right? Okay. Now when the producer complete the feeding of the buffer 1 and the producer start to filling the buffer 2. Okay. Now in this case, okay, so the consumer pulling the buffer and find out, oh, buffer 1's available. So then the consumer can actually copy buffer 1, copy the data from the buffer 1. And then when the consumer actually complete the buffer 2, and then the consumer just happened to complete the copy of buffer 1, so then the consumer can actually copy the buffer 2. And in the meantime, the producer can fill buffer 1. Okay. So both the consumer and the producer are busy. When the consumer is actually copy the buffer 1, the producer is feeding the buffer 2, and when the consumer is copy the buffer 2, and the consumer is feeding the buffer 1. Now, hopefully, feeding buffer 1 and feeding buffer 2, and feeding buffer, and also copy buffer 1, and feeding the buffer can take approximately the same amount of time. So in this case, both consumer and the producer are busy, except for the initial time, right? Now that's the advantage of using two buffers, and that's called buffer swapping. It's very efficient. Now, a circular buffer is a fixed array of buffer slots filled by the producers and emptied by the consumer, one slot at a time in the ascending order modulo the buffer size. Okay, so that means instead of using two buffers, you actually have an array of buffers. Okay, an array of buffer slot. So 1, 2, 3, 4, 5, 6, 7, da da da. Okay, so you may have like a total of n buffer slot. Okay, so 0, 1, 2, 3, da, 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 all the way to m minus 1. Okay, so a producer and a consumer can share a circular buffer to account for different rates of data production and consumption. Okay, so initially, so the buffer is, the buffers are empty. So all the buffer slots are empty. So both are point to the first one. When a producer actually produce anything, for example, produce and fill the first buffer, so then the cursor move to the next one, right? And then producer can produce next one, okay? And produce the next one, produce the next one, produce the next one. So the cursor gonna actually, for the producer, you're gonna move the, move to here. Okay, so that's a producer side. And then the consumer can start to consume the data. For example, the consumer gonna consume the data and consume another one, and in the meantime, the producer can actually keep going and continue to produce more, and the consumer gonna basically chase the producer. So in circular way. Okay, so the producer gonna move to the next here, and the consumer can actually move the cursor, forward. Okay. Now, using a circular buffer, we can actually solve some kind of issues, like if a producer and a consumer share a circular buffer, but the producer and the consumer gonna actually running at the different rates. Okay, so for example, in the first scenario, the data actually will be produced, for example, in bursts. Okay. Okay. So the producer starts by generating a burst of data items. Okay. So if you use only one buffer, then if you produce a burst of data items, then you only fill in one buffer, and you have to wait the consumer to, remove the data. So there's no way you can produce like 3 items in a very short period of time. So in that case, suppose I have a circular buffer, right? 1, 2, 3, done. Okay. So if the producer can, produce a burst of data, like suddenly produce 4 items, and then producer may actually stop over here, and then the consumer may slowly, so here's the producer, and the consumer may actually slowly, consume the data. 1, 2, 3, 4, okay, and then the producer can actually, again, there's a next burst. The producer can produce some data at a very fast speed, and then later on, the consumer actually follows the producer, but at the much slower rate and remove the data, remove the data, remove the data. So producer and consumer, operate at the different rates. Producer is, you're gonna actually, it's kind of burst in natural. So you're gonna produce a burst of data items, and the consumer can slowly do this. Okay. Now there's another scenario. So then the data consume, okay, at is called coarser granularity. Okay. So here's the producer. Okay. And the consumer. So the producer can actually produce the data 1, 2, 3, 4, 5, and then suddenly the consumer just come here, just suddenly just to actually, just to consume all the data at a very fast rate. And then the consumer can actually slowly gonna produce the data, in a circular way. Okay. And then the consumer comes back and just remove the data. Okay. So these are two different scenarios. So, but anyway, using the circular buffer, you can actually resolve some kind of issue of different, operation rates between producer and the consumer. Okay, so far we have talked about a buffer, right? So the buffer is used between the consumer and the producer. It's shared between producer and the consumer to store the temporary values. Now, the buffer has different meaning. Okay, a buffer actually used for caching holds a temporary copy of data that already exists on the disk. And in this case, it's called a cache. Okay, now, so let's talk about disk block caching. Now, so to speed up access to disk blocks, the modern disk controller includes an internal cache to hold the most recently accessed blocks. Okay, let's see. Suppose we have a disk. Okay. So a disk may have various different blocks, right? And then here's a disk block, or disk controller, I'm sorry. The disk controller may have various different registers, operands, opcode, or whatever, and there's also a buffer, right? And also there's a dedicated buffer space called cache. Okay, now cache is actually used to, to hold a most recently accessed blocks. Okay, that's an internal cache in the disk controller. Okay, now here's the application. And so here's the main memory. Okay, so the main memory also has a large cache. It's much larger than the cache, internal cache in the disk controller. Okay, now when the application triggers wants to actually, access a disk space and copy some blocks into the memory. So when application wants to do this, copy data, right? The application first gonna trigger the, disk driver. It's a piece of program that operate on the read and write on disk, right? So that's the piece of software. Okay, so the disk driver gonna actually, basically gonna check the write the parameters to first to check the busy register to see whether disk is busy, and if it's not busy, then write the parameters, write the opcode, and then eventually the disk controller basically copy the data from the disk to the buffer, right? Okay, let's say we have a disk here. The disk, we have a block, and there's another block, and another block, and another block, a couple of different blocks. So the application triggers the disk driver, and disk driver actually tried to actually communicate with the controller, set up the parameters, set up the opcode. So the controller actually start to copy the data from the disk, okay, to the buffer, right? And then set up the status and set, just to actually, change the busy register to say, okay, I'm available. So disk controller basically, tell the disk driver either from interrupter or using the polling or whatever. So the disk driver start to actually copy the data from the buffer, okay, from the buffer to the memory, right? Okay, so the data will be copied from buffer to the memory. So now, before actually the driver actually does this, so the driver first gonna actually make a copy of this block in the cache of the disk controller, in the cache area of the disk controller. Okay, so that data, the block 1 data is cached, and then this data, before it actually copied to the main memory, it's also cached in the main memory. Okay, so I use this color. Okay, it's cached in the main memory. Okay, and then copied to the main memory location. Okay, so the data, so the block 1 data, so over here, this data is cached over here and also cached over here before it actually copied to the main memory. Now, what's so good about a cache? Now, if we use caching, so if the application decide to say, okay, I want to copy another data, okay, so let's copy the other data to the buffer. So, okay, so let's say copy other data to the buffer. So second data is copied to the buffer. Okay, so before it copied to the buffer, and then it's actually also cached over here. Okay, and then it's also cached over here. And then the data is actually copied into the main memory. Okay, now what? Now if the application decide that I want to make the copy, I want to copy the data in the disk block 1 as 0, the first disk block. Okay, that's disk block 0, 1, 2, 3. Again, to the main memory. Now, when the application decides to do this, the application gonna first check the memory cache to see whether this data is actually in the cache. It find out, oh, it is in the cache. So, and then it directly copy the cache into the memory space. Okay. So you don't have to go all the way to the disk driver and copy the data from the disk space to the buffer of the disk controller, and then from the controller then copy to the memory cache, copy to the memory eventually. If that data is still in the cache, then you copy the data from the cache into the memory. So that's the purpose for the cache. Now, if the cache in the memory is, in the memory does not contain the data for the block 0. For example, this is gone. Okay, now this data is gone. It's not there anymore. Okay, not there anymore. And I want to copy data, and then it's going to trigger the disk drive, and disk drive are going to actually first, before make the copy from the disk to the buffer, it's going to check the cache over here. Okay, and find out, oh, this piece is actually in the disk controller cache. So it can actually basically copy this data from the cache into the main memory. Okay, from the cache into the main memory. And then first to the cache of the main memory, and then to the main memory. Okay. Okay, so that's the purpose of cache. Sometimes you're going to save a lot of operation, because when you actually copy the data all the way from the disk block to the memory, it's very costly. But copy the data from the cache of the memory to the memory, it's very fast. Okay, or from the cache of the disk controller, it's slower than copy from the cache to the memory, but it's still faster than direct copy from the disk block. Okay, so that's the purpose for the block caching, disk block caching. Now, as was mentioned in the previous slide, since a disk block cache can contain a large number of blocks, typically a hashing function is used to organize blocks into separate lists for faster access. You have to use the hash function. In addition, all blocks are divided into several categories and are linked together using separate linked lists. Okay, now these are three categories. Okay, now blocks critical to performance, for example, blocks used internally by the operating system must remain resident at all times, are kept on a list of locked blocks. Okay, so that's called locked blocks. Blocks expect to be accessed again in the near future. Okay, so then resides in a list that implement the least recently used policy. Okay, whenever a block is accessed, the block is moved to the rear of the list, and the blocks not accessed again gradually migrate to the front of the list and are removed when free buffers are available. Now, why is this? Because using least recently used policy, it means that if a block was accessed recently, and most likely it will be accessed again. So we should keep that, block in the cache. Okay. So, and then blocks expect to be accessed only once or very infrequent. Okay. For example, block containing file control blocks, which are accessed when the new file is opened and then it will never be used, are basically added to the front of the same least recent control list. And so if it's on the front, then it will be removed quickly. So because this block will be only used once. Okay. So let's take a look at the example. Let's draw the hashing table to illustrate how this disk block caching is used. Now, since a disk block cache may contain many disk blocks, a hashing will be used. So let's say here's the hash table. Okay, it may contains n different hash value, so h1 all the way to hn. So then we have h1, h2, and then the h5 and h6 and the h7, H8 and H9 and here. So all block numbers are hashed on value H1 through Hn. Okay, all block numbers are hashed on values H1 through Hn. The blocks are kept on lists based on the hash values. So a block is actually on one of the list based on the hash value. Okay, for example, the block with the hash value H2 will be on that list, like a B21, B22, and a block B23. Now these blocks have the same hash value H2. Okay, now here's the block with hash value H5, B51. And then we have a B71, B72, and a B73. Now, there's only one block with hash value H9, so that's B91. Okay. Okay. Now, in addition, all blocks reside on one of the several other lists. Okay. So one of the lists is called the locked list. It's called locked list. Okay. Now blocks that must not be removed from the cache. For example, these are very important blocks, right? Reside on the locked list. So they should not be removed. Okay. Now let's say, suppose B71, B51, B21, these three blocks should not be removed. So they should be on the locked list. Okay, so here's the locked list. Okay, so then let's say okay, they're linked. Okay, so that's a list. And then other blocks reside on a doubly linked list. Okay, now sorted in LRU order. So LRU, which means the least recently used. Okay, so since it's doubly linked list, okay, doubly linked list, so there's a LRU front and also LRU real and LRU front. Okay, I use the, let's say, green color represent LRU list. Okay, so the block at the front of the LRU list is the least recently accessed block. Okay, for example, B72 is at the front of the LRU list. Let's say B72 is at the front. Okay, linked to the LRU front. And then B72 is doubly linked with the B22, doubly linked, doubly linked, doubly linked. The reason we use doubly linked is because you can search this very easily, from front to the real and from real to the front, either way. Now B91 is at the real of the list. Okay, so B91 is the most recently, accessed block. But this B71 is the least recently accessed one. So, the least recently accessed block, like a B72, okay, so will be evicted from the cache if list of the free buffer is empty. So whenever there's a additional disk block is accessed and there's no free buffer, then B72 will be evicted. So this reminds us that there's another, so the free buffers are kept in a separate on a separate list. Okay, here. Now, when a block, for example, like a block 23, B23, okay, when block B23 currently reside in the cache is accessed again, okay, so that means one of the applications just accessed the B23 again. So then we should move B23 to the real of the LRU list. Okay. So in that case, we have to disconnect these, LRU real to the B91. So B91 is no longer at the real, B23 is. So then we're gonna, link this over here. Okay. So actually, let me actually erase that one. Okay. Also, you're gonna actually disconnect B23 with the B22 and the B73 because B23 has removed to the real, right? So now you're gonna directly connect B22 with the B73, and then connect the B23 with B91. Okay. So now B23 is the most recently accessed block. Okay. Now, when a new block, for example, is accessed, now suppose that new block has hash value H5. So then we're gonna actually put this new block in that list, right? Okay. So if a free buffer exists, so we can actually get rid of one free buffer and then just move it here. Okay. So a free buffer is allocated and a linked into the corresponding hash list at H5. Okay, in this case. Now, if the new block is not expected to be referenced again, so this is actually a new disk block. It's referenced, right? But it's not expected to be referenced again. So that means you don't need to put this B52 at the real of the LRU list. Okay, you should put this at the front because you should be immediately evict this block should be immediately evicted if it's necessary. So that means you have to update the LRU list. Okay, now so I'm gonna put this at the front and then connect to B72. Okay, so so that means instead of you can actually next one should be removed, the block should be removed is the B52. Okay, now in the last scenario is that the one block B21, which is on the locked list, is no longer needed. For example, the operating system released the locked buffer, so the corresponding buffer is unlinked from the current list and returned to the list of free buffer. Okay, so now in this case it's removed, right? So you can remove this from here and then return to the free buffer. Okay, so now let's see, we can remove this. Okay, so B21 is removed. Okay, so this is how we're gonna operate on a disk block cache we use hash table, and also use a separate free buffer. Now, if we have the free buffer is empty, then you have to evict one of the block on the hash table. Thank you.